So welcome back to a new session of the bank seminar. Today is a pleasure to introduce Yoshihiro Tonegawa from the Institute of Science in Tokyo, and he will tell us about the mean curvature flow with irregular forcing terms. So please.
Thank you very much for the invitation. It's a pleasure to give a talk at this seminar series. Can everybody hear well? Totally fine. Okay. Okay, so today I'd like to talk about this topic. I've been working for quite a while, this mean curvature flow with some irregular forcing term. And so I have been working on this something called the Allen-Kahn energy or molecular motor energy. And as I was working on this direction, I encountered various problems, and this one is actually one of the sort of a branch of what I've been working on. And so this is a joint work with many people. I mentioned my collaborators along the way. Okay, first off, I start with something very simple. Okay, so now I'll be looking at, in general, a family of smooth n-1 dimensional surfaces, M sub t in Rn. And so that's a geometric object, which is typically a codimension 1 surface. And this is now parameterized by time t, and it's called a mean curvature flow, which is abbreviated as MCF. Now, if the normal velocity of this surface motion is equal to the mean curvature vector of the surface itself, and let me write the normal velocity as v, it's a vector, and h is a mean curvature vector of the surface moving. Okay, and now this is a parabolic problem, as many of you probably know well already, but so you can actually do the following, that is, you give a smooth surface with, let's say, no boundary, compact, let's say, to make it easy, given a smooth compact surface M0, there exists a smooth solutions until some singularity happens. So if you are given some nice surface, then according to this motion law, this surface evolves in time, but it eventually collapses to a point, or you may have some kind of singularity, such as pinching off and others. And and well, by the way, the motivation of studying this can be many. You can associate this problem as more like a gradient flow of the surface energy. So okay, if you're given for example, this problem can be motivated from, say, plateau problem, that is a very important problem, of course, in geometric analysis. And anyway, so going back to what I was saying, so if you may have some singularity in as it evolves. So a lot of effort has been put into this notion of mean curvature, which is a sort of weak solution or generalized solutions. There are many kinds. One most famous one is perhaps level set flow. That's studied by Evans and Giga, no, sorry, Evans, Sprague, and Giga Goto, and others. And there's also this notion called the bracket flow, which was invented by Bracke in 70s, so that's a while ago. And also there's some others such as BV flow and many others, in fact. And the relationship between them are actually one of the interesting research field, because the correspondence between them is not entirely clear quite often. And there's also no uniqueness typically. And So it's very, and also this once you start having singularity, then um, the also just like plateau problem, you have to really think about what kind of surfaces you're working with in some sense, whether you be looking at the oriented surface or you're looking at the surface as a set and so forth. So you also have to worry about what kind of class of surfaces you be interested in to study. So the problem is not so simple. Okay, and then okay, so now there's this problem that of this existence part and as well as regularity theory. But the one that I like to focus today is something that really has been studied little, I would say, along this line. And I think really due to the fact that the construction of the solution is actually quite tricky and not so easy. So I think very little is done about these things that I'm going to talk about today. So it's the following problem. It's actually easy to describe by itself. So suppose you're given not just the initial surface M0, but you're given some time-dependent vector field. You can look at the one that doesn't depend on time as well, but just to be more general, I would be interested in the vector field, which is given and depend on x and t. So it's really a vector field. Um, so example I have in mind, and this is actually the place where I got this problem first. The example is, for example, velocity field of fluid, such as the velocity field coming from, say, solution of the Navier-Stokes equation or Euler equation. Okay, so this vector field is sort of, you think this as given. Well, okay, some problem, it's not actually given, it's part of the problem, but just uh, for now, let's say it's a given vector field. Now, so the question I'd like to pose is the following, that is, when do we have a flow of surfaces satisfying this velocity is equal to mean curvature plus this given vector field. Okay, so the motion law is slightly changed now from mean curvature flow to this motion law, where not only the surface move by mean curvature, but also you have this flow field which pushes these surfaces along the, as it moves. So, and I'll be interested in the, say, existence and also regularity and, if possible, uniqueness and so forth. Okay, so that's the sort of question I want to ask. Okay, so now why am I interested in this? The motivation could be many. Just I list a few that I can think of. Okay, the first and perhaps more broadly speaking, this may be motivated just by saying that, okay, this is like an analogy with a heat equation with inhomogeneous term, in the sense that, see, the velocity is like a time derivative. If you let the surface to be a graph, that's a time derivative. So it's like derivative with respect to time. And H is a mean curvature, so it's like a Laplacian, that is the sum of the principal curvature. So it's like a Laplacian. So this V equal to H itself is like a heat equation. Now, if you think about heat equation as a PD problem, you naturally think about the case when you have an inhomogeneous term. I mean, sort of things that when you learn heat equation, you also study this type of extra term that you put in a heat equation. So from that point of view, it's certainly mathematically natural object to study. By the way, this perp sign is a projection to the normal direction, by the way. Sorry, I forgot to explain this. But you see, the vector field may not be normal, of course, to the surface. So you'll be this v is supposed to be a normal velocity. So you might want to project this vector field to the normal, to the surface. Okay, so that's what it means. Okay, so that's the first one. Um, and also the second motivation I wrote this is a vectorial prescribing culture problem. So what I mean by this is that traditionally people study the constant mean curvature surfaces. For example, that is the mean curvature is constant. Okay. Now that's very much studied, and also you might study the so-called prescribed mean curvature problem where you are given a value of the mean curvature at a point and then look for a surface whose surface mean curvature is it takes the precisely prescribed value at that point. Now here, if v happen to be zero, this means if it's not moving, okay, so v equals zero means it's not moving, then this is actually surface which has prescribed mean curvature vector at a given point in some sense. Okay, so this could be the way to find the surface where you'll be interested in finding the surface which has this mean curvature vector having precisely the normal component of the given vector field. Okay, so this is something that I think again also not so studied. I think because this problem is not so it's not like variational problem. It's not like a constant mean curvature surface where you typically can prescribe the including the enclosed volume and you can minimize it. But in this case, it's vectorial, so you don't have that kind of formulation. Okay, so that's I think one of the reasons it's not studied. But I think it's not so natural to think about this because if you have certain say field or force field, and then if you have some surface whose surface tension is trying to balance with this force field, like electric field, for example, or so forth, this is not totally um, a natural problem, even though it's not studied so much. Okay, so that's could be another motivation. And also the third I list this as is that it's to study by studying this I think that there is a possibility that you may have a better understanding of the notion of velocity itself in some sense in the setting of geometric media theory. I feel that this is also not so well studied. I think that is if you are looking at the problem where the surface is moving, the notion of velocity can be actually something that's non-trivial. I mean, there are many ways to, in fact, define the notion of velocity. So somehow having this kind of a bit more analytic input, I think, gives you some better understanding, I think. Okay, and the fourth is, in fact, the fourth is the one that I got into this problem. This is there's a natural coupled problem of two-phase Navier-Stokes equation of and so let me just since I got this problem from this, maybe I just say a word about this. So okay, so the one that I was this was actually suggested by Chun Liu at in Chicago right now, but. So suppose you have fluid with two phases. This is would be a like Navier-Stokes flow field, and suppose you have a certain region. Let's call this ET, which is changing in time, and your surface is the boundary of this domain. So MT is the boundary of this ET, and then one can look at this more like really a toy problem, I would say, but just for me, I really find it interesting. So U is a flow field satisfying the usual Navier-Stokes with some extra terms. So this would be, I think, I think most of you know what this is. This is like the left-hand side of the Navier-Stokes, where P is a pressure and also this incompressibility condition that's divergence of u is equal to 0. Now the right hand side has this extra term which is so-called surface tension effect coming from this boundary. Okay, so this is very much well-studied problem when you have this two-phase this phase boundary, or maybe you could be looking at like some two-phase object, and then this boundary is exerting some force to the fluid through the surface tension. Okay, so h of n minus 1 is actually n minus 1 dimensional house of measure. So it's a surface measure on MT, and h is a mean curvature of this surface, this MT, and then divergence free. Now, here is another motion law of the surface, that is the velocity of this MT. Now, if C2 is equal to 0, yeah, okay, so suppose this is 0, then it just says that, okay, the surface is moving with the velocity of, flow field. But now if you have C2, you have this sort of extra mean curvature motion. Okay, so that's you take this as a motion law of this phase boundary. Actually, there is some problem if having this extra C2 H term, because if you do this, then it's not going to be, I mean, the enclosed volume is going to change actually. So that it's not going to be so-called conservative. I mean, the volume inside of the phase is not going to be conserved. So that's a bit of a problem, but just as a mathematical problem, still it's okay. Okay, so now this one has this nice energy law. It's very easy to check. You see, Navier-Stokes equation, if you don't have C1 and C2, this is very well known. Kinetic energy of fluid. Let's use L2 of U, L2 of U squared. If you take a time derivative of this, of course, it's going to be U dot ut. Now, forget about C1 term for now. Then you just use this equation, and then you end up having just only this Navier U square as a dissipation term. That's Navier-Stokes. But if you have this extra surface tension, then actually you have this extra term, okay? Now the time derivative of this is going to be equal to minus velocity of the motion of the, velocity of the motion, and dotted with mean curvature. That's the so-called first variation formula of the surface energy. Now, if the velocity equal to this, you just plug in this term. Okay, so you get this term coming from, I guess, this, and then the next term comes from this. No, sorry, I guess this. Sorry, ut term, okay, comes from this, I guess, and then you plug in this v, and you get this, and then this h, this term actually cancels. Okay. This term cancels, I guess. Yeah, this, oops, sorry. Not so good at this. And then it comes out to be this two term as a dissipation of this energy. So as a system, the sum of the kinetic energy of the fluid and the surface area is actually decreasing. Okay, so each of them may not be decreasing, but some of them are decreasing. So that's the system. And now, I was initially interested in this problem, and I did work on the how one can get the existence of this surface. Um, but actually, it turned out that fluid part doesn't quite help you so much. So after a while, I start working uh, in the setting where the velocity field is actually given. Just, doesn't have to be a solution of something, but it seems like that's somehow Navier-Stokes equation, okay, may give you this energy bound, but that's about all I can get, at least for now. So I start thinking, that maybe I just think vector field to be a given ones, then try to show the property of this moving surface. Okay. Now, to do this problem, there are many challenges. Okay, so suppose you're given a vector field, you're given an initial surface. Now, if this vector field is not so smooth, it's not even clear your initial surface is going to, for example, have a finite, surface area, because the fluid can mess up the surface, very, we can, it probably the surface may become very irregular if the flow field is very regular. So keeping the surface area as it evolves is not even very clear. Okay, and also the so and also note that if U is not so regular, then you really have to define this U as a trace on this moving surface. If you think about it, I mean, to define this velocity, you have to define this velocity on the surface. But if this velocity field is not regular, for such as say solar space, for example, then you have to define it as a trace. But that's also moving. Okay, so that's another challenge. And also, this problem unfortunately has definitely a non-uniqueness, because if this vector field is, for example, let's say, okay, Helder continuous only, then, and suppose sort of silly problem of this surface being flat. Okay, so just no mean curvature, zero mean curvature. Suppose you have this V, which is just Helder, then the problem becomes just a plane moving according to this velocity field. Now, it becomes just ODE problem, where the velocity field is actually just held there, and it's ODE. And it's a very well-known fact about this ODE, that you need vector field to be at least like C1, right? No, sorry, Lipschitz, right? To have a unique ODE solution. So if you go below Lipschitz, then you typically would not expect this, say, problem to be unique even. Okay, so but if you're looking at, say, fluid flow, then you don't usually, okay, as long as you're working with, say, weak flow field, say, like Lulé-Hoff, Lulé solution, then you don't want that to be like typically, you don't work with Lipschitz glass. Uh, in that sense, there's an apparent no uniqueness of the problem, but there may be some selection principle, even with a low regularity, like Dipel-Diom's type, sort of extra renormalized solutions, for example. So there might be some possibility of doing that kind of things as well. But anyway, so there's a lot of challenges in this problem of this surface evolution with this kind of irregular flow, sort of background flow field. Okay. Okay. So yeah, maybe I just state uh, what we could do so far. Not, I mean, it's not totally satisfactory, unfortunately, but I have worked on this for like maybe 10 years now. So up to this point, whatever I know, I want to describe this. So it turned out that there's sort of a subcritical case and a critical case. So first, I'd like to tell you what subcritical case is, which is PD point of view, somewhat natural. I'll tell you why. But now here is assumption first, sort of precise statement. Suppose that E0, this domain, given as an initial domain, is a bounded domain. Let's say it doesn't have to be bounded, but for simplicity, let's say it's a valid domain with a C1 boundary, M0, just as we had in the picture. And suppose, okay, this looks slightly bad, but I'll explain this. So I can work with this class at least, that is this vector field U. Okay, so this is a vector field that's I've been telling you about, not a regular one. U is in LQ with respect to time, and in with respect to space is W1P. That is the gradient is in LP, but LP norm is in with respect to time is LQ. Okay, so that's what it is. And but Q and P are sufficiently large, at least. That is Q, this is Q is exponent for time, is bigger than 2. By the way, 2 is more like a dimension of time here. So Q bigger than 2 means slightly bigger than the dimension of time. And the P is bigger than this NQ over 2 times Q minus 1. Okay, so it looks like a sovereign exponent. And in case of n equal to 2, additionally, I need this p has to be bigger than or equal to 4 over 3, therefore technical reason. But anyway, so where does this exponent come from? Okay, so that's not so difficult to say. Actually, it comes from just a parabolic scaling law. So it's not so surprising. Now, this problem is certainly parabolic in nature. So where if you want to see a scaling law, you do let x tilde to be lambda to the minus 1 times x, and then t tilde to be equal to lambda to the minus 2 times t, just to this change of variable. And then, and also note that the u is more like a velocity. Okay, so u is velocity, so velocity should behave like x over t. Okay, so velocity is x over t. Yeah. So the change of variable for u should be like u tilde is equal to lambda times u. Now, if you do this change of variable, this LP norm, as I said, this is W1P norm. That's a space derivative raised by power P. And then, so this is a LP norm of gradient. Now you take Q's power with respect to time. It's easy to check that this, under this change of variable, you end up having this exponent here. And basically, this being less than or equal to 0, which implies it's subcritical in some in this sense, is really this condition. Okay. So this condition is really telling you that if your vector field is subcritical, it's satisfied. Okay. So now, so what okay, sorry, I think. Yeah, so now you can't solve this directly with this low regularity, but basically, okay, so this is sort of very rough strategy of doing it, but at the end, what we can prove is that there exists a sort of generalized global in time solution to this surface evolution. Okay, so that's a bit old results, but that's the first things I don't know really I couldn't find any other reference on this problem actually. If you know, if you happen to know it, I'd like to know it, but at least as far as I look for, couldn't find anything. But anyway, so there exists a surface evolution, actually global in time, so it exists for all time, and it goes through various potentially singularity. Um, and there does exist solutions, which I'll explain what the definition of the solution is now, but which is relatively good property, the one with a relatively good property. Okay. So maybe at this point I stop and field some questions if you have any questions.
Any questions? Yeah.
So is there a way, the question is this flow, flow with the forcing term U perpendicular, is this a generalization of those usual flows with forcing terms? I mean, there's, for example, volume preserving mean curvature flow, and the forcing term is, it depends on the surface evolution. And my question is there a way to write down this equation as a special case of H plus U perpendicular?
Yeah, the voice is not so clear. Unfortunately, I can't discern the detail of the voice. Sorry. Yeah, could you kind of come to the mic? Maybe that's pretty better. Yeah.
Is it better now?
Yes, yes.
Okay. My question is, if this flow that you're presenting here, this H plus U perpendicular flow, if this is a generalization of the class of globally forced mean curvature flows. For example, the volume preserving mean curvature flow contains, instead of U perpendicular, it contains something like average curvature. And my question is if it is possible to write down these globally forced terms as a special case of your flow.
Yes, that's my first answer would be at least I don't know how to do it. It's a note that the U is a vector, and so there may be some way to feed back sort of this vector to be, for example, like volume preserving in sort of a way. Uh, but here, in fact, this vector field in the setting that I'm explaining this, vector field has to be sort of defined everywhere, basically. I mean, at least in the neighborhood of the moving surface. So yeah, that's I would say it's slightly different direction. Yeah, it's if you want to do volume preserving, typically you would be um, subtracting, for example, average mean curvature as a scalar quantity in some sense. I mean, you'll be looking at the velocity, but you um, as a scalar velocity, and then you'd subtract the average mean curvature value from the speed of the motion. Then you would have a volume preserving. Yeah, here it's there may be some way to do it, but by itself, yeah, the simple answer is not so clear, I would say. Yeah. Does that answer the question?
Yeah, thank you.
Thank you. Yeah. Yeah, surprisingly, I feel like this problem is relatively natural, but it's someone not studied at all before. Yeah.
Anything else?
I have a question about the apparent non-uniqueness. Could you go a bit deeper on this? Because it is because of you get more regularity than Lipschitz, or because the extra terms with the surface area and so on help for proving uniqueness.
Well, I think it's yeah. So if you don't have a Lipschitz for you with respect to X, typically it seems like you really don't have a uniqueness in a usual sense. And yeah, so the surface, I mean, the mean curvature part does regularizing of the surface, I think, in general. But somehow, I wonder, that's a question. But um, this, yeah, this part I'm not so entirely clear. As I said, yeah, if you have just a flat plane, and if you have a velocity which is normal to this plane, and if it's if this v is just held a continuous function, then it's easy to have a plane which is just sitting or start moving at any time. It's like this typical ODE solution, yeah? Which is you get for held a continuous vector field. So that's a sort of silly example of non-uniqueness. But yeah, at the same time, you sort of expect that in suitable sense, you have a sort of generic uniqueness at the same time. I mean, if you have, say, some condition on the vector field, such as, let's say, divergence free, and also, I guess, yeah, it's for example, divergence free is a good one. And then you have this renormalized solutions. So, but for each given particular surface, I don't think you have uniqueness. But yeah, this one's really I have no sort of I can't make any advance on this in this direction, unfortunately. But yeah.
Thank you.
Okay, so I think you can go ahead.
Should I restart?
Yeah.
Okay, yeah. So let me continue with this. So as I said, so there's this given say C1 surface and also this vector field U with this class, then there is a solutions. Surprisingly, actually global in time too. So it exists for all time. And so this gets a little bit more technical here, but just I want to give you the what kind of notion of solution we have in general. Okay, so the precise statement is more or less the following. So what we say, what we call as a solution is the following. So we have this time parameterized sets of finite perimeter E sub t, and also radon measures mu sub t, where this radon measure is like a surface measure of this evolving surface. So instead of looking at the surface, we in geometry measure theory, what people usually do is look at the surface measure instead. So mu t is actually a surface measure, really. And with this motion law get satisfied. So, but now I just have to give you the first characterization. So mu is a radon measure, but this is some particular type, and mu zero is at time t equal to zero. You should start with this measure n minus one dimensional Hausdorff measure restricted to this initial surface. So it's really at t equal to zero, your measure is really the surface measure of the initial data. But later it may not be so clear. But one thing we know is that this mu t is so-called integral radon measure. Or so this mu t, I didn't write this, but mu t is in the form where it's like n minus one dimensional Hausdorff measure restricted to some n minus one dimensional rectifiable set. Actually, it's a rectifiable set is more like C1 surface, but slightly more generalized things. But this guy is at least integral. Yeah, we have also so-called integer multiplicity, but without going too much into the detail, this is really telling you that for almost all time, this evolving mu t is really like n minus one dimensional surface measure restricted to n minus one dimensional surface. Okay. And also this mu t has a well-defined notion of mean curvature vector, so-called generalized mean curvature vector, which you can define using first variation formula, which I again don't want to go into this too much, but so for this mu t, which is really is like a surface measure, you can define a well-defined you can define this notion of mean curvature vector, and it's L2 in space-time. So h square integrate with respect to surface measure, and you integrate over time. This is finite for all time, and this mu u can be in fact defined as a trace on the surface. Okay, so meaning on the surface, meaning you with respect to mu t. So as I said, this was one of the challenge that one has for this problem, but it's defined as trace and also with certain integrability, which I don't want to go into this, but this S turned out to be the sort of the right power for the Sobolev function in some sense. That is, if you are given a Sobolev function, you have a notion of trace on the surface, and you have certain integrability as a trace, but this exponent turned out to be the right ones, actually. So you have a well-defined trace, even though interesting thing is, this surface is actually really moving around, but you still have this sort of this type of bound. Now, so a bit more other things is that this number 4, again, without going too much, does tell you that the motion law is satisfied. Okay, so this requires some more explanation, but this is really telling you how, now by the way, phi is the non-negative test function. So phi is any function but non-negative with compact support. This number 4 is really telling you how the surface energy, surface measure changes in time. Okay, so note that this T1, T2 are different 2 times, and T2 is later time, T1 is before. So the difference between these 2 time can be bounded from above by this right-hand side. And it happens, so this formula, if you've never seen this before, it's a bit difficult to see, but this here is the number that this part describes the velocity of the motion. Okay, so if you have a regular surface motion, this inequality is satisfied with equality actually. With here, you should have a velocity field. Okay, so this motion law, having this number 4 is really telling you that the surface is moving with a velocity equal to h plus u pipe actually. Okay, so this is a weak formulation, more like a brackets formulation. So bracket flow is described in this way. So sorry, I think if you've never seen this, it's a bit too quick, but just I want to emphasize that this inequality actually really is a way to describe that motion law is satisfied. So if I had more time, I'd like to explain this more in detail, but just to give you some idea. Now, as we had these 2 objects, that is this moving domains, ET, but also surface measure. Now, the relationship between them is as follows. So the VV norm of this moving domain, this is this is more like surface measure on this boundary is bounded from above above by this surface measure, and in fact, if everything is fine, they are supposed to be equal, but there's a possibility that they could be different. Okay, so that this is satisfied. So, and in addition, again, I'm sorry, this is a little bit technical, but another motion law that's satisfied is in this sense that if you take a distributional derivative of the characteristic function of this domain, ET, moving domain, that is equal to H plus U dotted with the nu. Nu is the outer unit normal vector, which is a unit normal to the set of finite perimeter. Okay, so this is satisfied in a distributional sense. So this again is another way of describing that this boundary is moving by the motion law of velocity equal to h plus u. If you, yeah, so that's all satisfying. So all these things are, I just mentioned some names, but maybe I just move on. And these are the last three properties. There are more actually. I'm sorry, but yeah, there are many things, but just the main things. And we also know that um, for there's some sort of short time, maybe it's a long time, but at least we can make sure there's a short time such that mu t is precisely of this form. Mu t is precisely equal to this form, and MT is actually at least in this class C1 in time, and Helder C1 alpha, let's say, hypersurface in the parabolic sense. So there's certain regularity for a short time, and yeah, and also it's a strong solution during this time. We know that it's a strong solution in a PD sense. So you can write this surface for short time as a graph, and then this motion law is satisfied in a PD sense as a strong solution. Okay, so this is also not so easy to prove, but you can do it. If you happen to have more regularity such as Helder, then actually this short time regularity become better, like C2 beta, say. And then once you get to there, then it's a really classical setting. But anyway, so you have some regularity. Okay. So just a remark is that uh, there's very much this some critical cases somewhat close to the pure mean curvature flow, in the sense that without this extra term, you have just mean curvature flow, and there are a lot of things to know about mean curvature flow, and a lot of things go through um, for this subcritical case. And as I mentioned already, I would be very interested to know any selection principle, such as like some analog of dependent ions, perhaps. Um, but I have no idea about this one. So, okay. Let's see. So, just I go through no idea of how you go through the proof, at least for this one. There's other ways to do this too, but for first I try to do this. So the idea of proof uh, is one way is to use the so-called parabolic Alenka equation of this type. Now, without this term, extra term, that's very much studied by many people, and it's known that it converges to mean curvature flow. With this extra term, uh, as far as I know, I don't see any work done in this direction. So anyway, so we did this way, and so for mean curvature flow, there is this very well-known so-called Huskins multiplicity formula, and which I don't want to go through this, but so it's actually important to get the in this even without this extra term, having the Huskins multiplicity formula it turned out to be very important. But with this extra term, there's an added difficulty, and okay, maybe how many minutes do I have? Like 10 minutes at use. Maybe we started a bit later, I guess, but
Well, yeah, 15.
okay, maybe we have, let's say 15, 10, 10, 10, 15 minutes, I guess. Yeah. Okay, okay. Um, yeah, so let's see. So there's this kind of here, what I found is that, as I said, one of the difficulty I had was to prove that you can have trace of this vector field on the surface. Now, to do this, one important ingredient is so-called this Mayer-Zimmer's theorem, which I think it seems like it's not so well known in this in our even in our community. Is the following fact that if you have a radon measure mu or Rn, and assume that this mu has this bound, is that this is like if you look at the ball radius r, measure how much you have mass there, divide by r to the n minus 1. Now you move around this ball. Suppose that this is bounded. So it's really is like saying that this surface, this mu is like a surface measure of a nice surface. Okay, so then this quantity will be bounded. Now, if you have this bound, then you have this inequality actually. Note that this is phi is integrated over the surface. Just think this mu as a surface measure. Okay, here I think it's easier that way. So the surface measure of surface integral of this function phi, you can bound this by this right hand side. This c is a dimension dependent constant times this quantity, Cm, this quantity, times the Vivino, or the L1 of the gradient. So here, this is a surface integral. That's integral with respect to the Lebesgue measure. Okay, so you can actually bound the sort of like a trace integral on the boundary, for example, in terms of the gradient, but with respect to this integration with respect to the Lebesgue measure, okay? As long as you have this quantity bounded. So this surface, this boundary doesn't have to be regular at all. Okay, it could be very bad, very irregular. But as long as this quantity is bounded, you have this nice formula. Okay, so that's a very nice way of controlling the integral on the surface in terms of the value outside, okay, of this. Okay, anyway, so I take advantage of this, and somehow, so the trick of the important part of this theorem was to get this bound with respect to so-called diffused surface energy. So for this Allen-Khan equation, there is a natural surface energy associated with this Allen-Khan. It's like a modica mortora energy here. Now, so that's like a surface energy divided by RT minus 1. So if this one is bounded, then you have this type of control, and then you can actually control this extra term coming from this extra U term. Okay, so one of the key estimate was this one, and so there's a lot of sort of detail that you have to do, but the basic key idea is getting this type of things and then controlling this extra term. Okay, so then that's sort of kind of things that one does. Okay, just for the next 10 minutes or a few more minutes, I want to say a few words about this. Let's see, so-called critical case. By the way, one thing which I wasn't so happy with this result was the fact that this exponent evades a very important sort of uh, case that I wanted to study first. So note that in the previous, where was it? No, I guess here. You see, for this coupled problem, note that this nabla U was only L2 in space-time. If you integrate this in time, you have this L2 of gradient U. Gradient U is bounded in space-time in L2. And also gradient, sorry, the other natural bound you get is the kinetic energy is bounded in time uniformly. Okay, so because if you integrate in time, then this quantity is bounded in time, right? So that's a natural class that you might want to look at. And then note that this quantity here, U, Q cannot be 2. Q equal to 2 is not possible because of this. And also, if Q is equal to 2, note that if it's 2 here, here's a 2, and then n, so 2 n, so n equal to p is going to be a critical case. Okay, so for example, if its dimension is 2, n equal to 2, if n is equal to 2, then this 2 cancels and q is equal to 2. Then p equal to 2 is also not included, right? With this exponent. So p equal to 2, q equal to 2 is not included in this. So even for dimension 2, this result does not gives you this this bound. Okay, so this nabla U L2 in space-time was not possible. Okay, so I was not so happy about this. I didn't know how to handle this case. But now, just recently, or okay, now it's like about more than a year ago. But at least I could handle this critical case. So I just wanted to tell you this. Yeah. Okay, so that's a work I did with Yunin Liu at NYU. So this is something that I was very happy to be able to do. In fact, because I didn't know how to do it for about 10 years. So now assumption is that suppose that E0 is open set with countable. Well, okay, just forget about some detail, but just think this E0 to be some domain, for example, with, if you like, it's say C1 curve. Okay, so this is just a C1 curve is fine, but it can be more general. Okay, so but with finite length. And then suppose that you have this U is in this class, that is U is it's L infinity in time, but in L2. So L2 norm of the U is bounded in time. Okay, so it's exactly the sort of one that I was talking about with Navier-Stokes coupling. Okay, and also gradient U is L2 L2, so that's like the square of this number U is integrable with respect to space-time. Okay, so that's exactly the class that comes naturally from the Navier-Stokes equation in 2 dimension. So that's again also, as I said, it's a critical case. Okay, particularly this part. Okay, so this part is not so clear what that critical is, but at least okay, we assume this. And so let CT to be this. So the assumption is that these quantities are bounded. Okay, so that's L2 norm of space. Sorry, L2 norm of U is bounded in time, and also this gradient U is L2 in space-time. Okay, so as I said, it comes Navier-Stokes coupling 2 dimension. You get this naturally. And conclusion is that there exists a global in-time solutions of this problem. Okay, so even for critical case, you have at least a solution. This is like an evolution of curve, okay, under this fairly irregular class of flow field. And it exists for all time, in fact. So to me, it was a bit surprising, at least. It's not clear it's if such things exist or not a priori at all. So was to me, I feel like it's a very interesting result. Anyway, so again, the characterization of the solution is very similar as before, in fact. So I probably don't want to repeat the whole things, but again, we have a family of, in this case, like a one-dimensional curve, one-dimensional measure, mu t, and also set of finite period et. And initially, you have the prescribed measure. And actually, in 1D case, you have this extra sort of characterization that is, in fact, I know that, sorry. In fact, I know that they are like, for almost all time, it's a embedded W22 class. So it's actually, it is a nice curve with second derivative in L2 and of this form, in fact. So it's a bunch of just embedded curves, okay, moving in time with mean curvature in L2, and then this U, which is a trace, again, as it said, it's a trace on this moving curve, belongs to L2. And number 4 is exactly the same as before. It tells you in this generalized sense that the curve is moving at the velocity equal to h plus u, okay, u perp. So this number 4 is really a characterization of how things is moving. And note that you see h squared is here. So you know this right-hand side is finite also. And here is the same again. The relationship between this the boundary measure is less than or equal to the surface measure in general for all time. If nothing happens, then they are supposed to be equal, but they could be different. Okay, and also this distributional characterization of the motion of the bound domain is also given as well. This is actually new result by Tashiro, right? One of my students. Okay, so now I think maybe for this critical case, unfortunately, for subcritical case, we had the short time regularity. That is, we knew for short time, it's a PD strong solutions for some short time. But for this one, nothing is known so far as I know, or I don't think it's not known. So it's not even clear if you start out with smooth curve, for example, what happens immediately after. Even that's not known. Whether it's going to stay as a graph, even. It may not stay as a graph, actually. So as far as I know, I'd be very interested to know, let's say, okay, suppose your curve is a graph. Is this going to stay as a graph for a short time? Yeah. So I mean, then the level of knowledge I have is so little here at this point. So anyway, so the proof is totally different from subcritical case where I use the Allen-Kine equation. Actually, I don't know how to use Allen-Kine in this case. So some very rough idea of the proof is the following. So this all comes down to some realization as follows. So it's actually very special for 2D somehow, and I don't think you can do it for higher dimensional. So but the idea itself is relatively simple, and so now it comes down to this formula that is suppose that mu has okay, here I don't go into much, but for this mu you can talk about the so-called generalized curvature, mean curvature or generalized curvature, in this case 1D. Then we have this monotonicity formula. This is very special for 1D case. Okay, that is this density ratio can be bounded by this right-hand side. That is, this is total curvature, raised by power 1/2, and then the L2 of curvature. Okay, so this is very special for 1D, and yeah, and then this gives you you see this bound. This gives you this allows you to that mean to use the Mayer-Zimmer inequality. So this U square can be bounded by using this quantity and times the gradient of U square integrated over the Lebesgue measure like this. Now you have this guy. Now, okay, so I don't want to go into this so much, but it's actually there's an easy way to do this a priori estimate like this. This is first variation formula. Now velocity is equal to h plus u, so you just substitute h plus u, and then do Cauchy-Schwarz, and then and so forth. And the point is, oops, sorry. Now you bound this down. That's the difficulty we have. Okay, to control. So, but now this one is controlled by this here by this. So you use this, and at the end, you end up having this type of ODE. So the time derivative of this can be bounded the mu-t itself. Okay, with this suprema of u and number of gradient u. Okay, so and this is the same formula. Now you integrate in time, you get this formula. Okay, so the logarithm of the total measure has this differential inequality satisfied. Okay, so that gives you the total measure bound in time. And actually, this is something that is needed. Once you get this, then you can control the other terms and so forth. And the way you construct this is another story, but somehow you have some machinery to construct some approximate solutions once you have this type of a priori bound, actually. And so, this part, I think I'll just skip it, but okay. This estimate is actually quite tight. It's somehow to me looks kind of miraculous that this works, but yeah. Anyway, so nothing further property is not known about these solutions. It's a one-dimensional curve evolutions, which I believe it's very sort of simple if you think about it. It's just people, study curvature flow of curves and in great detail, but once you put this irregular vector field, then nothing is known so far. Okay, so I think I went over my time. So here I'd like to stop and thank you for the attention. Yeah.
Many thanks for your nice talk. And now it's time for questions. Well, let me start with one. So I have actually two questions. So one is that if something is known about the volume preserving versions of your force flow, and second, if you know something about fattening effects.
Okay. Actually, could you hold on? I have to move to other place. So just 1 minute, please. Just sorry. Yeah. Okay. Let's see.
Um,
Sorry. I have to move. Yeah. Sorry, could you say again? Actually, if you speak close to the mic, I think it's easier to understand. Yeah.
So my question was if there are fattening phenomena in your flow, and second, if there is something known about volume preserving versions of the flow.
Well, fattening, no, actually. At least I know that solution stays surface measure, so there's no fattening. The solution itself doesn't fatten, but yeah, this of course depend. This has to do with the non-uniqueness as well. So I might be looking at just one solution, with places where fattening is happening, in fact. So yeah. But this solution itself stays like hypersurface-like for all time. So in that sense, no fattening. Okay, so that's the first question. And then as for the volume preserving ones, yeah, as I said, this one's a little bit difficult to think in that sense because this vector field has to be defined basically everywhere, not just on the surface, but a priori, this vector field has to be given on a ambient domains. So in that sense, maybe there's some way to incorporate the effect to keep the volume preserved in a suitable sense, but actually I don't know. Yeah, it might be interesting to think about this. Yes. Thanks. Yeah.
Yes, it's raising the hand, so can you ask the question?
Yes, I have a question. It's I guess it's an expected question. Since you have a solution for all time, can you say something about the asymptotic behavior as time goes to infinity? Maybe if you have
Yeah.
just a constant vector field, for instance.
Oh, constant vector field. Yes, I think, okay, first, Alf, I actually haven't really studied that aspect, but yeah, I think it's interesting to see it. Let's see, in general, okay, maybe constant is somewhat special case, but I think the energy estimate that we get is that the surface with this type of very regular vector field at least. Okay, so maybe that's not what you're thinking, but if you are given just arbitrary ones with this low regularity, the surface measure typically can exponentially blow up actually in time, okay, unless you have something extra. Yes, so the a priori estimate we get is of the exponential type, where the volume can blow up in time. Yeah. So, but depending on what you do, particularly like a coupled problem where you have some a priori energy bound, for example, like the one that I discussed at the beginning, this two-phase flow field, for example, that may have some something there. Yes, yeah. But yeah, it's an interesting questions. Yeah, as I said, very little is known about any of this problem. So. Yeah, you can ask any question, and there's no one knows that. No one knows the answer.
Thank
Yeah,
you.
very nice to see you again. At the end.
Yeah, nice to see you. Thank you.
Okay, great. So that means that you have lots to study about this problem. So I guess that's all. So let's thank again Yoshi for the nice talk of time.
Yeah, thank you very much for the invitation.